Let us see the selection criteria for primitive polynomial of order 4. So order 4 means 5 bit representation. So numbers 16 to 31 are represented with 5 bits. So first we will see what is the selection criteria for the primitive polynomial, that it should be a prime number and it is irreducible over Galois field 2, because primitive polynomial we are using to construct the extended field. So here the extended field is Galois field 2 raised to 4, that is Galois field 16. So first criteria is that you have to search for the number with 5 bit representation which is a prime number. So here order is 4, that means 5 bit representation. So number 16 to 31 are represented with 5 bits. So among 16 to 31, prime numbers are 17, 19, 23, 29, 31. So these are the numbers with 5 bit representation. So 17 is represented as 10001, and you know how to write the polynomial. So this if 5 bits are there, so this bit corresponds to the degree 4, that is x raised to 4, its coefficient is 1. This is the bit position, this is the position for x cube, x square, x and 1. So wherever 0 is there, you are not going to consider that term, because 0 means coefficient is 0. If coefficient is 0, that term cancelled out. So here x4 plus 1, here x4 cube square is not there, so x plus 1. Here x4 cube is not there, x square, x 1. Then x4 x cube x square plus 1. Then x4 x cube x square x plus 1. So these are the prime numbers. Now amongst these prime numbers, you and their polynomial representation, which is so you are getting the polynomial of order, that means highest degree equal to 4. So amongst these polynomials, we have to see which one is irreducible over Galois field 2. That means which polynomial has no root in Galois field 2. What does it mean? It means that if you put either 0 or 1 in that equation, you are not going to get 0. That is, it is irreducible over Galois field 2. That means it has no root in Galois field 2. So for example, if this is the equation x raised to 4 plus x plus 1, so in Galois field 2 the elements are 0 and 1. So if you put 0 here, you will get 1. That means 0 is not a root of x4 plus x plus 1. If you put 1, so 1 plus 1 plus 1, 1 plus 1 is 0, and 0 plus 1 is 1. So you are getting 1. So 1 is also not a root. So it is irreducible. For example, this one, x4 plus 1. So here if you put 0, you will get 1. So so 0 is not a root. If you put 1 here, then 1 plus 1 is 0. So 1 is a root. So it is not irreducible. So the trick is that you have to see for, so you know that if there are odd number of ones, you are going to get the XOR operation equal to 1. If there are even number of ones, then you will get XOR equal to 0. So the same trick we are going to use here. So if it is a 0, if you put 0 in either of the equations, you will get 1 only. So 0 is not a root in any case, because this one is not affected by 0. So 0 is not a root in any of these equations. So we are not going to consider 0. In case of 1, you know that even ones are going to give zeros and odd ones are going to give 1. So the same criteria we are going to use. So we are counting how many number of terms are there. So here terms are 2, so 1 plus 1 is 0. So it has 1 as a root, so it is not irreducible. So here odd ones you are going to get 1 plus 1 plus 1, so that is equal to 1. So it is irreducible because you are not going to get a 0 here. If you put here 1, so 1 plus 1 plus 1 plus 1, 4 ones are there, so answer is 0, so 1 is a root. It is not irreducible. Here 1 plus 1 plus 1, so it is also 0, so 1 is a root, so it is not irreducible. Here 1 plus 1 plus 1 plus 1 plus 1, that is 5 ones are there, so the answer is 1. So 1 is not a root, so it is irreducible. So in simple we can say you have to see how many terms are there. So here the terms are 2, so this is not irreducible. Here the terms are 3, so it is irreducible. Here terms are 4 in both these equations, so it is not irreducible. Here the terms are 5, so it is irreducible. So that is a simple trick to find whether it is irreducible over Galois-Field 2. But you have to see that 1 should be there. So if at the last there is 1, then only you can use this criteria. So the x raised to 4 plus x plus 1 and x raised to 4 plus x cube plus x square plus x plus 1, these are irreducible over Galois-Field 2. So the two conditions are satisfied here, that these two equations or these two polynomials have no roots in Galois-Field 2. That means if you put 0 here, you will not going to get 0. If you put 1 here, you will not going to get 0. That means 0 and 1 are not roots of x raised to 4 plus x plus 1. Also 0 and 1 are not roots of x raised to 4 plus x cube plus x square plus x plus 1. So these are irreducible over Galois-Field 2. Also they corresponds to prime numbers. X raised to 4 plus x plus 1 is 19, and x raised to 4 plus x cube plus x square plus x plus 1 is 31. So these are prime numbers as well. They are irreducible over Galois-Field 2. So either of these can be used as primitive polynomial to construct Galois-Field 2 raised to 4, that is Galois-Field 16.